Heat. Heat, usually denoted by the symbol capital Q, is non-mechanical energy transferred between objects or systems due to a temperature difference. Being a form of energy, the unit of heat is the joule. A system does not contain heat, but it does contain internal energy. If heat is added or removed from a system, it is the system's internal energy that changes. Heat, like work, only exists during the process of transfer of its energy from one system to another. Heat is energy in transit. Heat, Q, can be signed, hence positive or negative. We may regard Q as always added to a system, such that if Q is positive, then positive energy is added to the system, and if Q is negative, then positive energy is removed from the system. Adding a negative quantity is equivalent to removing a positive quantity. Alternatively, we may regard Q as always positive, so it is then the magnitude of the signed quantity, and state explicitly whether it is added to or removed from a system. We say that heat is added or absorbed or gained if energy is added, and that heat is removed or rejected or lost if energy is removed. You may assume that Q is signed unless stated otherwise. We have seen previously in mechanics that work can be regarded in the same way. Work is mechanical transfer of energy, and if it is signed, then doing positive work on an object adds kinetic energy, and doing negative work on an object removes kinetic energy. A common unit of heat is the calorie, or cal for short, equal to 4.186 joules, to 4 significant figures. This is the quantity of heat needed to raise 1 gram of water by 1 degree centigrade or 1 Kelvin. This brings us to the concept of heat capacity. An object, or a body or a system, has a heat capacity, capital C, defined as the heat needed to raise its temperature by 1 degree centigrade or 1 Kelvin. If you know the heat capacity, C, of an object, then to raise that object by a temperature delta T requires Q equals C delta T joules. Conversely, to lower the temperature by delta T requires Q equals C delta T joules of heat to be removed from the object. To be precise, let the change in T be defined as delta T equals T final minus T initial, or more concisely, Tf minus Ti. Then for an increase in T, delta T is positive, and for a decrease, it is negative. Then Q equals C delta T is the signed heat added to the object. Alternatively, we may define delta T as the magnitude of T final minus T initial, and then Q equals C delta T is the positive quantity of heat that must be added for an increase in T or removed for a decrease in T. Rather than knowing the heat capacity of an object, it is often useful to know the specific heat capacity C, noted as small or lowercase c, of a substance, which is defined as the quantity of heat needed to raise 1 kilogram of that substance by 1 Kelvin. The specific heat capacity, usually just called the specific heat, is the heat per unit mass per degree, or said another way, the heat per kilogram per Kelvin needed to raise the temperature of 1 kilogram of a specific substance by 1 Kelvin. Given a mass m of a substance, to change its temperature by delta T requires Q equals mc delta T joules of heat to be added. The specific heat of water is 4.19 kilojoules per kilogram per Kelvin, to 3 significant figures. Note that each phase of a substance has, in principle, a different specific heat, so it is more accurate to describe specific heat as a property of a substance in a certain phase, whether solid, liquid, or gas. A gas is also called vapor. Ice, which is the solid phase of water, has specific heat 2.10 kilojoules per kilogram per Kelvin, and steam or water vapor has specific heat 2.00 kilojoules per kilogram per Kelvin. Here are a couple of examples. First example, how much heat is needed to raise 5 liters of water from 20 degrees centigrade to 65 degrees centigrade? We use the formula Q equals mc delta T. The mass of 5 liters of water is 5 kilograms. C is 4190 joules per kilogram per Kelvin. And the change in temperature delta T is 45 degrees. So we get a result of 943 kilojoules of heat. Second example, find the specific heat capacity of aluminium, Cal, that is in the solid phase, if 182 kilojoules of heat are needed to raise 2 kilograms of aluminium by 100 degrees centigrade. We take the formula Q equals mCal delta T and rearrange it to solve for Cal as Q divided by m delta T. And putting in the numbers, we find that the specific heat of aluminium in the solid phase is 910 joules per kilogram per Kelvin. We will be studying gases a lot. And for a gas, it is often more convenient to work with the molar heat capacity rather than the specific heat capacity. The molar heat capacity, with symbol capital C, is defined as the quantity of heat needed to raise 1 mole of a substance by 1 Kelvin. It has units joules per mole per Kelvin. Both the specific and molar heat capacities may be used for solids, liquids, and gases, but in the laboratory it is easy to measure the mass of a solid or a liquid, but not easy to measure the mass of a gas. However, it is fairly easy to determine the number of moles of a gas if we know its volume. Be careful not to mix up capital C for heat capacity of an object with capital C for molar heat capacity. As always in physics and maths, be careful to define what symbols mean and then use them consistently.